Okay, so in this series of videos, we follow the Ch.8, the source of magnetic field. Okay, so in this picture, we show you the maglev trend. Okay, so this maglev trend, it is a trend in China that can exceed a speed limit of about 600 kilometers per hour. It's very fast. Okay, so why is it so fast? Because they use the principle of electromagnets. Okay, so they use the electrical power source to create a magnetic field, and from these electromagnets, they have kind of like force pushing each other, so causing the levitation or keeping the train up, and with the train, with the weight of the train mg, and with the force that push the train up, it will decrease the friction force. So without the friction force, the train can move very fast. Okay, but the principle behind it is they use the electrical power source to generate the magnetic field. So we have the concepts here. The important concepts here is that the current can generate the magnetic field. Okay, so the principle about current generates magnetic field. So it just like the analogy with the principle that charge can create the electric field. So in this equation, this is a Coulomb's law. So Coulomb's law is the equation that we talk about source of electric field that can generate electric field or electric force. But in this handout, we are talking about magnetic field instead of electric field. So for the magnetic field, the source of magnetic field is the current. So if you have current, you always have a magnetic field according to this equation called Biot-Savart's law. So in this handout, we are applying this equation into some different applications. So we start with considering just a current in form of the straight wire, and let's see how the magnetic field, how large the magnetic field is generated from this source. Okay, then we try to change our source into a ring, so the ring with the current flowing through it, and this ring is also can generate a magnetic field. Okay, and the magnitude and the directions of magnetic field can be calculated using Biot-Savart's law. So the applications that you can see from this system of the ring, the current ring, the coil that can generate a magnetic field is the tangent galvanometer. So the tangent galvanometer, this instrument, we have these instruments in the PHY104 lab. Okay, you can go and have a try in this in this lab. It's quite fun. So the principle is we have a coil, which is the current ring up here, and then the current ring will generate some magnetic field in this direction, and the magnetic field generated this way can cause the change in the direction of the compass. Okay, so it will make the compass to rotate along the magnetic field, and you can use this principle to measure the magnetic field of Earth. Okay, and then we come to talk about the cases of infinite wires. Okay, so for example, if I have two parallel infinite wires, which in first case we put the electric current I1 and I2 in the same direction, and the second case I put electric current I1 and I2 in opposite direction, and we are going to see what are these electric fields, what are these electric currents going to do to each other. So we are going to prove that for I1 and I2 going into the same direction in parallel, and there will be forces that from I1 that come from the magnetic field of I2. So I2 will create a magnetic field in this direction. Okay, and then when you have the magnetic field in the out direction, and you have the current I going past through this magnetic field, what happened with your I is there is going to be the force that push the upper wire towards the lower wire. And also, if you try to do the same thing, you are going to have another force that is pushing I2 towards I1 as well. So when you try to apply the same rule, you are going to see I1 and I2 that going to opposite direction can generate the forces that push them out from each other. So in this way, you can control the force between the wire with current by controlling current direction, and you can control the force. And then we come to consider the Amperes Law. So the Amperes Law is a shortcut to consider the Biot-Savart's law for some special case. Okay, so it is analogous to Gauss's law. So this equation is Gauss's law. So for Gauss's law, we have some systems, those are in symmetry, and then we can solve for electric field very quickly. Okay, so in this Amperes law as well, we have the system that has symmetry, and then we can solve for the magnetic field very easily for some of those systems. Okay, so this system consists of the wires that is infinitely long. So we have this minus infinity and infinity. We can calculate the magnetic field very easily. So if I want to consider the point R, using the Amperes law, I just bring the left hand side to be b times by the circumference of this circle, 2 pi r, and then I have mu I, so that I can solve for the b pretty easily. And then for another case of the solenoid, so the solenoid is the coil of electrical conductive wire like copper. Okay, and we make the coil to be in the cylindrical shape. Okay, so in this way, there will be amount of current that flowing in this direction, and it can generate the magnetic field through along the direction of the solenoid. Okay, and from Amperes law, you can also calculate the magnetic field from this very easily. So from the left hand side, I just times magnetic field with the length of the solenoid, and on the right hand side, I just times the current by the number of turns. Okay, so like in this example, 1, 2, 3, 4, you consist of 4 turns, so n is equal to 4 in this case. Okay, and then you can solve for the magnetic field inside the solenoid. And for the final case, you are considering a big wire. Okay, so this has electric current flowing through it, and then in the same fashion as the Gauss's law. In Gauss's law, you consider the charge enclosed in a Gaussian surface, but in Amperes law, we consider just only the current that those are in the Amperes loop. Okay, so we call this the Amperes loop. Okay, and we are going to consider this amount of current as I enclosed, or IENC, and then my Amperes law equations will be b times 2 pi r and is equals to mu I enclosed, and then you solve for the magnetic field. Okay, so here is the introduction and the summary of what we are doing in this handout 8. Okay, we starting with consider Biot-Savart's law, consider the source of magnetic field from the current, in which we are going to derive the magnetic field from the straight line, the magnetic field from a ring, and then when we consider infinite wire, what if we put two wires, one case with the current in parallel, and another case with the current anti-parallel, and then we consider the Amperes law, in which we are consider some cases such as if we have the infinitely long electric wire, and then if we have solenoid, and if we have a thick wire, and try to calculate the magnetic field inside and outside.